Hello and welcome to Slow Orbit, where we explore the wonders of the universe at a pace that lets you relax, unwind, and reflect. If you're new here, make sure to hit that like button, subscribe, and join our growing community of space enthusiasts. And while you're at it, let me know where you're watching or listening from. Whether you're gazing up at a clear night sky or maybe listening as you drift off to sleep, it's fascinating to think about how we all share the same dark sky, no matter where we are. Today we're diving into one of the most intriguing questions in all of astronomy. Why does the night sky stay dark? With so many stars out there, why isn't the entire sky lit up, like a cosmic blanket of light? It's a paradox that has puzzled thinkers for centuries, and in this episode we'll peel back the layers of cosmic mystery, exploring everything from the very origins of the universe to cutting-edge theories that continue to reshape how we understand the vastness of space. So grab a cozy seat, and let's embark on this journey to the edges of the observable universe. The night sky has always held a special place in human imagination. For millennia, it has inspired wonder, awe, and even fear. We look up and are confronted with a vast, sparkling expanse that feels infinite, filled with stars that seem so distant, yet somehow so close. It's a sight that has been described in poetry, studied by scientists and painted by artists throughout history. The mysteries of the sky have shaped religions, guided explorers, and given us a sense of our place in the universe. But despite the beauty and vastness of the night sky, one question remains a constant puzzle. Why does it stay dark? This paradox is something that has perplexed thinkers for centuries. As we gaze upward, we see only a fraction of the stars in the universe, but the sky is not illuminated by them. Even though the stars are innumerable, it feels as though their light doesn't quite reach us. It's a question that leads us to one of the most intriguing and thought-provoking dilemmas in astronomy. If there are so many stars, why is the night sky not filled with light? This mystery was first seriously questioned by the German astronomer Heinrich Wilhelm Olbers in the early 19th century. Olbers famously posed what came to be known as Olbers's paradox. If the universe is infinite, with an infinite number of stars, why does the night sky remain dark? Surely if every direction we looked was filled with stars, there would be no dark patches. Yet when we look up, we see not a sky full of light, but a sky full of darkness, dotted with points of bright stars here and there. Olbers' paradox challenges our fundamental understanding of the cosmos. It's one of those questions that seems deceptively simple on the surface, but is deeply tied to the very nature of the universe itself. What Olbers didn't know, and what we have come to understand through modern science, is that the answer is not just about the number of stars, but about the nature of space, time, and the universe's origins. Over the centuries, many thinkers have attempted to solve the riddle. Ancient Greek philosophers such as Anaximander and Democritus were some of the earliest to speculate on the nature of the cosmos, long before Olbers. Anaximander, in the 6th century BC, suggested that the stars were small, distant objects, and that the universe itself might be infinite. Meanwhile, Democritus, who lived around the same time, theorized about the existence of countless worlds, each with their own stars. These early ideas set the stage for the more refined scientific theories that would emerge much later. However, it wasn't until the 17th and 18th centuries that a more precise understanding of the problem started to form. As telescopes improved, astronomers began to discover more about the vastness of the universe, yet the paradox remained unresolved. By the early 19th century, when Olbers presented his famous question, the paradox was already beginning to take shape as a key issue in the field of cosmology. It was Olbers's insight that truly brought the mystery to the forefront. If the universe was static and eternal, filled with an infinite number of stars, Olbers argued, we should be surrounded by an unbroken glow of light. But instead we see the vast, starry night punctuated by deep black spaces. He couldn't explain why this was the case, but he understood that something about our perception of the universe and the stars was flawed. This question has since led to many breakthroughs in astronomy. Today we know that the universe is not static, but expanding, and the stars that we see, though countless, are not distributed evenly throughout the universe. The dark sky we see today is a result of the finite nature of the universe itself, the age of the cosmos, the speed at which light travels, and the vast distances between stars and galaxies. But Olbers' paradox was one of the key challenges that helped push scientists to rethink the nature of the universe, ultimately leading to the formulation of revolutionary ideas like the Big Bang theory and the concept of cosmic inflation. The dark sky, far from being a flaw in our understanding, is a clue that has guided the development of modern cosmology. It tells us that the universe is not just vast but dynamic, changing and expanding in ways that we are still only beginning to understand. This paradox that Olbers first posed has since become a gateway into deeper questions about the structure of the cosmos, the limits of the observable universe, and the very nature of light itself. As we continue to explore these questions, we will uncover more about the forces that govern the stars, the galaxies, and the dark spaces between them. The night sky, with its mystery and allure, holds the answers to some of the universe's deepest secrets. But to unravel those secrets, we must look beyond what we see with our eyes and understand the universe as it truly is, a vast, expanding, and ever-changing expanse, full of both light and darkness. In the chapters ahead, we'll explore how the science behind Olbers' paradox has evolved, from early astronomical observations to the cutting-edge theories that continue to reshape our understanding of the universe, from cosmic inflation to dark energy and the limitations of light itself. We'll take a closer look at how these discoveries contribute to the mystery of the dark night sky, and what they tell us about our place in the vast cosmos. The idea that the night sky should be bright instead of dark has its roots deep in the philosophical and scientific discussions that stretch back centuries. In fact, the origins of Olbers' paradox can be traced to early thinkers who pondered the very nature of the universe and the stars that filled it. One of the earliest philosophers to entertain such ideas was Giordano Bruno, a 16th century Italian thinker whose views on the cosmos were revolutionary to say the least. Bruno suggested that the universe was infinite, and that it was filled with an infinite number of stars, each with its own planets. His ideas were quite bold for his time, as they contradicted the more commonly accepted views of the cosmos, which saw the Earth as the centre of the universe and stars as fixed points in the sky. What made Bruno's ideas so radical was not only his concept of an infinite universe, but also his suggestion that stars were scattered throughout it, much like the ones we see in our own night sky. He proposed that the darkness we see between stars was simply the result of our limited view, not a result of any fundamental aspect of the universe itself. Bruno's thoughts laid the foundation for later developments in cosmology, though they would remain speculative for centuries, as his views were considered controversial and even heretical at the time. A few hundred years later, Johann Lambert, an 18th century German mathematician and philosopher, contributed another important piece to this puzzle. Lambert argued that based on the principle of an infinite, unchanging universe, the night sky should indeed be bright, if stars were distributed evenly across the cosmos. According to this thinking, every point in the sky should be filled with the light of a distant star. The very fact that the night sky remains dark seemed to defy the logic of an infinite star-filled universe. Lambert's thoughts would later influence Heinrich Wilhelm Olbers, a German physician and astronomer who in 1823 formally articulated the paradox that now bears his name. Olbers' paradox asks a simple yet profound question. If the universe is infinite, and if stars are scattered throughout it, why do we not see an infinite amount of light from those stars filling the sky? According to Olbers, if the universe were infinite, every line of sight would eventually meet a star. The sky, then, should be blazing with light, and not dark as we observe it. Yet the stars, while numerous, seem to light only certain pockets of the sky, leaving vast stretches of darkness between them. This is the paradox that has intrigued scientists, philosophers, and thinkers ever since. The paradox challenges some of our most fundamental assumptions about the universe. What does it mean for the universe to be infinite? What kind of structure could explain the darkness we see? Is the universe static and unchanging, as many thought for centuries, or is it dynamic, expanding, and evolving over time? Olbers' question, while seemingly straightforward, pointed to deeper issues of the nature of space and time, of the very fabric of the cosmos. It beckoned a deeper exploration into the nature of the stars, their distribution, and our ability to observe them. As the centuries progressed, answers to Olbers' paradox began to emerge, but not without controversy and debate. While some thinkers at the time, like Edwin Hubble and Albert Einstein, would soon help to establish that the universe was not static but expanding, the key to understanding the darkness of the night sky lay not only in the nature of stars, but in the very structure and history of the universe itself. However, even today, the paradox is a useful lens through which we examine the nature of light, the vast distances between galaxies, and the limitations of our perception. More recently, Tiziano Frasca, an Italian astrophysicist, has revisited the paradox with the tools of modern physics. Frasca suggests that quantum theories may offer new insights into the puzzle, suggesting that the behavior of light might not be as simple as previously thought. He explores how the interaction between light and the quantum properties of space itself could contribute to the perceived darkness of the night sky, even in an infinite universe. This contemporary approach reminds us that, just like the thinkers before us, we are still piecing together the grand puzzle of the cosmos, one theory at a time. What makes Olbers's paradox so enduring is its ability to blend philosophy with modern cosmology. At its core, the paradox questions not just the observable universe, but also the very assumptions we make about the nature of space, time, and light itself. It suggests that the answers to such questions are not simple. Rather, they involve a deep understanding of the universe's origins, its structure, and the limitations inherent in our ability to observe it. This paradox continues to challenge us today, as we uncover new discoveries about the nature of the universe, the role of dark matter, and the accelerating expansion of space itself. Every time we make a new observation, we get a little closer to solving the puzzle, but the night sky still remains dark, an enduring mystery, even as we unravel its secrets. In the early 20th century, the concept of a static, unchanging universe was beginning to show cracks. The idea of a universe that had always existed, unchanged and eternal, no longer seemed to match the growing body of evidence. Two scientists, in particular, helped push us into a new way of thinking about the cosmos: Alexander Friedmann and Georges Lemaitre. Both Friedmann, a Russian mathematician, and Lemaitre, a Belgian priest and astronomer, independently developed solutions to Einstein's equations of general relativity that suggested the universe was not static, but instead expanding. This was a groundbreaking realization. Up until then, the prevailing thought was that the universe was in a steady, unchanging state. But the mathematical models created by Friedmann and Lemaitre showed that the universe could in fact be expanding, with galaxies moving away from each other. Lemaitre's work was particularly influential. In 1927, he proposed that the universe began from a primeval atom, a single, incredibly dense point from which everything we see today originated. This idea was the precursor to what we now call the Big Bang theory. Lemaitre's insight laid the groundwork for what would later become the most widely accepted explanation of the origin and evolution of the universe. Friedmann, working with similar equations, also concluded that the universe must be expanding, though he was not immediately convinced of the Big Bang idea itself. Nevertheless, his work, along with Lemaitre's, helped shift the scientific community's perspective from a static universe to one in motion, continually growing and evolving over time. But it wasn't until the 1920s, when Edwin Hubble made his famous discovery, that the theory of an expanding universe was confirmed. Hubble observed that galaxies were moving away from us in all directions, and the farther a galaxy was, the faster it appeared to be receding. This phenomenon, now known as Hubble's law, provided the first strong evidence for the idea that the universe was expanding. Hubble's discovery transformed the field of cosmology, shifting it from one centered on static models to a more dynamic, evolving understanding of the universe. It was no longer a matter of debating whether the universe was expanding, but rather trying to understand the mechanisms driving that expansion, and the implications for the nature of space and time itself. But the expansion of the universe brought with it a new puzzle. Why doesn't this expansion mean that distant starlight should reach us more easily? After all, if the universe is expanding, surely the stars should be spreading their light further and further across space. The answer lies in how we think about space itself, and how light travels through it. This brings us to the research of Ruth Hayward, a contemporary astrophysicist whose work focuses on the effects of cosmic expansion on the limits of observation. Hayward's studies delve into how the universe's expansion alters our perception of distant light. As galaxies move farther apart, the light they emit is stretched or redshifted due to the expanding space between us and them. This stretching of light's wavelength means that light from distant stars and galaxies becomes increasingly harder to detect, as it moves through the ever-expanding universe. Hayward's research shows how, in an expanding universe, the farther we look, the less of the light from distant stars actually reaches us. As space itself stretches, it acts like an invisible barrier, making it difficult for light to travel across vast distances. This is a crucial reason why, even though the universe contains countless stars, the night sky remains dark. The light from many of these stars simply hasn't had time to reach us, and even if it has, the expansion of space has stretched it out of the visible spectrum, making it invisible to our eyes. This idea is closely related to the theories of Hermann Weyl, a German mathematician and physicist whose work on scale invariance had important implications for cosmology. Weyl suggested that the laws of physics should remain unchanged under transformations that alter the size or scale of the universe. This concept, though abstract, helps explain the nature of cosmic expansion. As space expands, the very fabric of the universe stretches, changing the scale of the distances between objects in the universe, including light itself. Weyl's ideas helped pave the way for understanding how the expansion of the universe could fundamentally alter the way light and other cosmic phenomena behave. The implications of an expanding universe are profound. Not only does it change our understanding of the cosmos itself, but it also has real consequences for why we see the night sky the way we do. As galaxies move apart, light from distant stars is stretched and becomes less visible to us. The expansion of space, the stretching of light, and the finite nature of the universe's age all contribute to the darkness of the night sky, despite the countless stars scattered across the universe. What all of this reveals is that the universe is not static as we once thought, but is constantly in motion. The stars, galaxies, and even the space between them are not stationary. They are stretching, evolving, and changing in ways that we are only beginning to fully understand. The dark sky we see above us is not a mistake or a flaw in our understanding. It is a direct result of the dynamic, ever-changing nature of the universe itself. As our knowledge of cosmology continues to grow, so too will our understanding of why distant starlight doesn't reach us, and why, despite the vast number of stars, the sky remains dark. In the mid-20th century, a revolutionary idea emerged that would fundamentally reshape our understanding of the universe's origins and its early development: cosmic inflation. This theory was first proposed by the physicist Alan Guth in 1980 as a way to solve some of the fundamental problems with the standard Big Bang model. While the Big Bang theory explains the beginning of the universe, it left some critical questions unanswered, particularly about its uniformity. Why is the universe so homogeneous, with galaxies and cosmic structures so evenly spread out? And how did the universe manage to expand so quickly, from a tiny, dense point to the vast expanse we see today? Guth's theory of cosmic inflation introduced a new idea. The universe, in its earliest moments, underwent an incredibly rapid expansion, far faster than anything we'd previously imagined. In an incredibly short span of time, fractions of a second after the Big Bang, the universe expanded at an exponential rate. To put it into perspective, imagine a balloon expanding at such a rapid rate that in the blink of an eye, it goes from being the size of a marble to being as large as the entire observable universe. This sudden, rapid expansion explained why the universe looks the same in all directions, and why it has the same fundamental properties across vast distances. Inflation theory also helps solve the flatness problem, which posed the question of why the universe appears so geometrically flat when, without inflation, it would have been far more curved. The exponential growth during inflation stretched space-time to the point that any curvature from the early universe was effectively smoothed out. However, Guth's idea didn't go without further refinement. Andrei Linde, a Russian-American physicist, expanded on Guth's original work in the 1980s, introducing what is known as eternal inflation. Linde's theory took the concept of inflation one step further, proposing that inflation didn't stop after the first fraction of a second. Instead, it continued in certain regions of space, leading to the creation of multiple pocket universes within a larger multiverse. According to this idea, the universe we see is just one of many, each with different physical properties and constants. The implications of Linde's work broadened the scope of inflation theory, showing that the universe we observe might only be one small piece of a much larger, ever-expanding reality. While inflationary theory has become a cornerstone of modern cosmology, it is still a subject of ongoing research and debate. One contemporary astrophysicist, who has contributed to expanding our understanding of inflation's effects, is Catherine Hamans. Hamans has explored how inflation not only stretches the universe, but also creates vast voids and cosmic structures that block light from certain regions. In her research, she highlights how inflation can cause the formation of large-scale cosmic structures, such as galaxies and clusters of galaxies, which can create shadows or gaps in the observable universe. These voids can make distant light harder to reach us, adding another layer of complexity to the already challenging task of observing far-off galaxies. While inflation theory provides compelling answers to many questions, it's not the only model of the universe's early history. Another fascinating perspective comes from Neil Turok, a physicist who has proposed a cyclic model of the universe. Unlike the standard model of inflation, which suggests a singular Big Bang event followed by rapid expansion, Turok's cyclic model suggests that the universe undergoes endless cycles of contraction and expansion. In this model, the universe doesn't begin and end in a singular event, but instead oscillates through endless cycles of bangs and crunches. Each cycle leads to a new Big Bang, giving birth to a new universe. This idea provides an alternative view of how the universe evolves and challenges the traditional idea of a single beginning point. Regardless of the specific model we follow, cosmic inflation plays a crucial role in our understanding of the universe's expansion and the darkness of the night sky. The rapid expansion of space in the early moments of the universe not only explains the uniformity we observe across vast distances, but also ties directly into why distant starlight doesn't reach us. As the universe expanded at such a fast rate, the distances between galaxies and stars grew at a rate that far outpaces the speed of light, meaning that the light from the earlier stars simply didn't have time to reach us. Furthermore, the stretching of space itself also stretches light, pushing it to longer wavelengths known as redshift. As galaxies move away from us, their light becomes increasingly redshifted, making it harder to observe those distant stars. This stretching of space caused by inflation ultimately limits the amount of light that can travel through the universe and reach our eyes. In other words, the very process that allowed the universe to expand and take on its current form is also responsible for the darkness of the night sky. The theory of cosmic inflation does more than just explain the universe's vastness and structure. It offers a framework for understanding the limitations of our observational reach. The universe's expansion, combined with the stretching of light itself, creates a situation where, despite the overwhelming number of stars, vast regions of space remain inaccessible to us. Light from distant stars and galaxies either hasn't had time to reach us, or is no longer visible to the human eye, as it is stretched beyond our ability to detect it. The continued exploration of cosmic inflation, along with the various competing models, invites us to keep pushing the boundaries of what we know about the universe. From Alan Gough's original proposal to Andre Lin's concept of a multiverse, and Neil Turok's cyclic model, each theory brings new insights into how the universe came to be and why the night sky remains as dark as it does. As our understanding of inflation continues to evolve, so too will our understanding of the universe's vastness, the nature of light, and the fundamental reasons why we can only see so much of the cosmos. The Big Bang theory is the cornerstone of our understanding of the universe's origins, offering a picture of how everything we see today began from a single, incredibly dense point, around 13.8 billion years ago. This explosive beginning set everything in motion, initiating the expansion of space itself and the creation of the building blocks of matter. However, the universe, in those early moments, was not the vast star-filled cosmos we observe today. It was far more hostile to light. The universe, in its earlier stages, was incredibly hot and dense, and the conditions were such that light simply couldn't travel freely. In the first few minutes after the Big Bang, the universe was filled with a hot, dense plasma of particles, mostly protons, neutrons, and electrons. This plasma was so thick that light couldn't escape. Instead, the free electrons were constantly scattering any light that tried to make its way through, creating a fog of sorts that enveloped the entire universe. This opaque state lasted for about 300,000 years, a period sometimes referred to as the Cosmic Dark Ages. During this time, the universe wasn't transparent in the way we're used to thinking about space today. Rather, it was a kind of cosmic soup, where light was trapped and couldn't travel across the vast distances we now associate with space. It wasn't until the universe cooled down enough for electrons to combine with protons and form neutral hydrogen atoms that the universe became transparent. This process, called recombination, allowed light to finally travel freely, leading to what we now detect as the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation is crucial because it provides us with a snapshot of the universe as it was just after the fog cleared, and it carries with it information about the state of the universe at that time. In the 1990s, two scientists, John Mather and George Smoot, played a pivotal role in confirming the existence and significance of this radiation. Their work with the COBE, Cosmic Background Explorer, satellite provided the most detailed measurements of the cosmic microwave background, offering us a glimpse into the conditions of the universe's earliest moments. Their data showed minute temperature fluctuations in the background radiation, providing evidence of the density variations that would later grow into the galaxies and clusters of galaxies we see today. But the cosmic dark ages weren't just about light being trapped. The early universe was also a place of tumultuous activity, with other processes shaping its structure and influencing the journey of light. One of these processes involved dark matter, a mysterious form of matter that does not interact with light, making it invisible to telescopes. While it remains unseen, dark matter has a profound effect on the formation of galaxies and the overall structure of the universe. Dmitry Klopov, a Russian astrophysicist, has contributed extensively to our understanding of how dark matter played a role in the very first stars. He theorized that dark matter could have influenced the rate at which gas collapsed to form the first stars, helping them ignite in the early universe. Dark matter, although invisible, interacts with regular matter through gravity, which means it can clump together and form structures that influence the behavior of ordinary matter. These gravitational effects likely helped seed the formation of the first galaxies and stars, marking the end of the Dark Ages. Yet, while the formation of stars and galaxies was beginning, the universe was still far from transparent in the way we see it now. The vast distances between these early galaxies were full of gas and dust that continued to scatter light, making it difficult for light to travel freely across the universe. Topological defects are another important feature of the early universe that might have had a role in shaping how light behaved during these early stages. These defects, discussed by physicist Alexander Vilenkin, are irregularities in the fabric of space-time itself that could have formed as the universe cooled and expanded. In some models, these defects are thought to be related to cosmic strings, hypothetical one-dimensional objects that stretch across vast distances. If they did exist, cosmic strings could have created regions where light was bent or blocked, adding further obstacles for light trying to travel across the universe. While these topological defects remain a speculative concept, they help illustrate the complexity of the early universe, where not only was light struggling to escape the dense plasma, but space itself was a far more chaotic and turbulent place than the calm expanse we see today. This was a universe in flux, with everything from the very fabric of space-time to the formation of the first stars contributing to the challenging conditions in which light could travel. As the universe continued to expand and cool, light eventually began to travel freely. But even then, it was not a simple journey. The early universe was still filled with vast amounts of gas, especially hydrogen and helium, and the light from the first stars interacted with these elements. This interaction would continue to affect the spread of light for billions of years. Over time, as galaxies and stars formed and began to emit their light, the universe slowly became more transparent, with the darkness of the cosmic dark ages receding. This era, while crucial in setting the stage for the universe we see today, highlights how the universe's early development was far from simple. From the opacity caused by the hot, dense plasma in the early moments after the Big Bang to the more complex interactions of dark matter, topological defects, and the first stars, the early universe was a place where light was constantly struggling to escape. Only after billions of years of evolution, through the processes of galaxy and star formation, did the universe become the vast, shining expanse that we now observe. Today, the cosmic microwave background radiation serves as a reminder of that early, opaque universe, and provides key insights into the origins of everything that followed. The universe's transition from darkness to light is a slow, gradual process, one that took hundreds of thousands of years, followed by billions more of cosmic evolution, And yet, even now, as we peer deeper into space, we're still seeing remnants of that early light, scattered and stretched across the cosmos. It's a light that has travelled for billions of years to reach us, still carrying the echoes of the Big Bang and the long journey from darkness to the vibrant star-filled universe we now see. The mysteries of the cosmos are not only bound by the vastness of space and time, but also by the strange and elusive rules of quantum mechanics. As we've seen, light has its limitations, especially over vast distances. But the way light behaves isn't always as straightforward as we might expect. In fact, the principles of quantum mechanics provide insight into why light doesn't always travel as we might intuitively think it should. At the heart of this complexity lies two key features: uncertainty and wave-particle duality. The Heisenberg uncertainty principle, one of the cornerstones of quantum mechanics, tells us that there are limits to how precisely we can know certain pairs of properties of a particle, such as its position and momentum. This idea isn't just a minor technicality, it fundamentally changes the way we understand the behavior of light and other particles. In the context of light, the uncertainty principle suggests that there's a fundamental fuzziness to the paths that photons, light particles, take across space. This means that light doesn't travel in a perfectly predictable straight line. Instead, it can scatter, curve, or even behave in ways we don't expect when interacting with matter or gravitational fields. Wave-particle duality adds another layer of complexity. In quantum mechanics, light is not just a stream of particles, called photons, but also behaves as a wave. This duality explains phenomena like interference and diffraction, where light can bend around objects or create patterns when passing through narrow slits. When light behaves as a wave, its path is no longer a simple line, but rather a set of probabilities that describe where it might go. This adds unpredictability to its journey, especially over great distances. So, when we observe light from distant stars, what we're seeing is not a perfect, clear signal, but a wave-like disturbance that has travelled through a chaotic and often unpredictable universe. These quantum features also affect how light interacts with the fabric of space-time itself. This is where Roger Penrose's ideas on quantum gravity come into play. Penrose, a leading figure in theoretical physics, proposed that the very structure of space-time might not be as smooth and continuous as we think. Instead, it may be quantized, meaning it could have a discrete structure at the smallest scales, much like how matter is made up of atoms. If space-time is quantized, then light might encounter tiny irregularities as it travels across the cosmos, potentially slowing it down or altering its path. Penrose's work challenges the traditional view of space as a smooth, continuous stage where light simply moves in straight lines, instead suggesting that the quantum nature of space-time could limit light's reach and influence how we observe distant objects. Another idea that stretches our understanding of the universe is the multiverse theory, as proposed by David Deutsch, a British physicist. According to Deutsch, the universe we observe may not be the only one that exists. Instead, there could be many different universes, each with its own set of physical laws. These universes, though potentially inaccessible to us, could have properties that affect our own universe, including the light we can observe. If multiple universes exist, the light from far-off galaxies might not reach us because it could be trapped in other realms, or follow paths that we cannot detect within our own universe. This idea opens up a new realm of possibility, suggesting that our universe might be just one of many, each with different rules, shaping our reality in ways we're only beginning to imagine. Building on these ideas, we also find a fascinating perspective in the many worlds interpretation of quantum mechanics. This interpretation, which proposes that every possible outcome of a quantum event occurs in its own separate universe, radically alters how we think about the cosmos. According to this view, the universe we perceive is just one of an infinite number of parallel realities. These worlds could exist alongside ours, each with its own version of events unfolding. If this theory is correct, it could mean that the light we see from distant stars is just a small part of a much larger multiverse, and other regions of reality might contain light that we cannot observe because they exist in different dimensions or timelines. One more intriguing theory that contributes to our understanding of the limits of light is quantum loop gravity, as developed by Carlo Rovelli. Rovelli's work proposes that space-time is not smooth and continuous, but is made up of tiny, discrete units, like the grains of sand on a beach. In this model, space-time itself is granular at the smaller scales, meaning that light may interact with these tiny structures in ways that we cannot currently detect. If spacetime is indeed granular, then light could encounter quantum fluctuations as it travels, which could cause it to scatter or distort. This could help explain why we can only see light from objects within a certain range, and why distant light might be distorted or even blocked by the quantum properties of space itself. All of these theories, quantum mechanics, quantum gravity, the multiverse, the many worlds interpretation, and quantum loop gravity, offer different perspectives on why light behaves the way it does across the cosmos. They challenge our understanding of reality itself, suggesting that the universe is far more complex than we could have imagined. Whether light is being scattered by quantum uncertainties, blocked by the structure of space-time, or limited by the existence of parallel universes, these theories help explain why we can only observe a fraction of the universe, even though light has travelled for billions of years to reach us. In the end, these ideas all point to a similar conclusion, that the universe we observe is not a simple, straightforward place. Instead, it is a realm shaped by quantum phenomena, where light and other particles follow paths that we can only partially understand. As our understanding of quantum mechanics and the universe deepens, we may one day discover even more factors that limit what we can observe, further expanding our understanding of the vast and mysterious cosmos we call home. In the early universe, long before the stars that we know today, there was a dark and quiet expanse of space filled with nothing but the simplest elements: hydrogen and helium. This era, often referred to as the Cosmic Dark Ages, lasted for hundreds of millions of years after the Big Bang. The universe was a vast, cold and empty place, with no stars to light the way. But then, something remarkable happened. The very first stars began to form. These stars, known as Population 3 stars, were unlike any stars we see today. Population 3 stars were born from the primordial hydrogen and helium that filled the universe after the Big Bang. Unlike modern stars, which are made up of a mixture of elements like carbon, oxygen, and heavier metals, these early stars were composed almost entirely of hydrogen and helium, with very little else. Because of this, their formation was vastly different from that of the stars we observe in our own galaxy. These stars were much larger, hotter, and more luminous than the stars that came after them, and they played a crucial role in shaping the universe as we know it today. The formation of these first stars is a process that scientists are still working to fully understand. One of the key figures in this research is Joseph Silk, a British astrophysicist whose work has focused on the early stages of the universe and the formation of the first stars. Silk proposed that these early stars formed in dense pockets of hydrogen gas that were able to collapse under their own gravity. As the gas contracted, it became increasingly hotter and denser, eventually reaching the temperatures needed for nuclear fusion to begin. These early stars ignited the process of reionization, which was one of the most important events in the history of the universe. Reionization refers to the process by which the ultraviolet light from these first stars and the first galaxies began to ionize the surrounding hydrogen gas, effectively clearing the universe of its earlier opacity. Before reionization, the universe was filled with neutral hydrogen, which scattered light and made it impossible for light to travel freely. As the first stars formed, their intense radiation began to break apart the neutral hydrogen into ionized hydrogen and free electrons, allowing light to travel more freely across the universe. This process helped shape the universe into the transparent cosmos we observe today. However, the formation of the first stars and their role in reionization were not just a matter of gas collapsing under gravity. There was another important factor at play: dark matter. Dark matter, which we can't see directly but know exists because of its gravitational effects, played a crucial role in the formation of the first stars. Stacey McGaw, an astrophysicist known for her research on galaxy formation and dark matter, has shown how the presence of dark matter in the early universe helped facilitate the collapse of gas clouds, allowing the first stars to form. Dark matter, although invisible, has mass and gravity, which means it could exert a pull on regular matter. This gravitational pull helped the gas in the early universe collapse more efficiently, leading to the formation of the first, massive stars. In addition to McGaw's work on dark matter, Tiziana Di Matteo, an astrophysicist known for her work on computational simulations of galaxy formation, has provided valuable insights into how the first galaxies were born. Di Matteo's simulations model the processes that led to the formation of early galaxies, showing how the first stars contributed to the development of complex cosmic structures. These simulations are crucial for understanding how the gas from the early universe clumped together to form galaxies, and how those galaxies eventually merged to create the larger structures we observe today. DiMatteo's research also sheds light on how the interactions between the first stars and the gas surrounding them contributed to the growth and evolution of galaxies in the early universe. Despite these groundbreaking insights, observing the first stars remains one of the greatest challenges in modern astronomy. These stars were incredibly far away, and their light had to travel across vast expanses of space, much of which was still filled with gas and dust that absorbed and scattered light. As a result, the light from these early stars is difficult to detect, even with our most powerful telescopes. Moreover, the light from these stars was stretched out by the expanding universe, a process known as redshift, which made it even harder to observe them directly. To make matters more complicated, the first stars also existed in regions of space that were influenced by the presence of intergalactic gas. This gas, which was part of the overall cosmic structure, absorbed much of the light from the first stars, further obscuring our view. As a result, the first stars are extremely difficult to detect directly, and scientists have to rely on indirect methods, such as studying the cosmic microwave background radiation or looking for the faintest traces of their light. Despite these challenges, astronomers are making progress in uncovering the secrets of the first stars. New telescopes, such as the James Webb Space Telescope, are specifically designed to peer into the distant reaches of space, where these early stars may have formed. By studying the light that has travelled for billions of years, scientists hope to learn more about the formation of the first stars, the role of dark matter, and how these stars help shape the universe we see today. The search for the first stars is not just about uncovering the origins of our universe, but also about understanding how the universe evolved into the starry, complex expanse that we observe now. These early stars were the first beacons of light in a dark and empty universe, and their formation marks a key turning point in the cosmic timeline. Understanding their origins and their role in the universe's evolution helps us answer fundamental questions about the universe's past and its future. In the early 20th century, Edwin Hubble's discovery of the expanding universe fundamentally changed the way we understand the cosmos. Hubble's observations showed that galaxies are moving away from us, with more distant galaxies receding faster than those closer to us. This discovery led to what we now call Hubble's law, which states that the velocity at which a galaxy recedes from us is directly proportional to its distance from Earth. Simply put, the farther away a galaxy is, the faster it appears to be moving away. This observation is the cornerstone of the expanding universe theory, suggesting that space itself is stretching, causing galaxies to move apart. Now, this idea brings up an interesting question. What does this mean for the travel of light across the universe? The answer is quite remarkable. As the universe expands, light from distant galaxies is stretched as well. This stretching of light occurs because space itself is expanding, and light, as it travels through space, is carried along with it. The further away a galaxy is, the more its light gets stretched, or redshifted. Redshift is the shift of light toward longer wavelengths, which makes the light appear more red. This is the opposite of blue shift, which occurs when light is compressed into shorter wavelengths, making it appear more blue. Redshift is a direct result of the expansion of space, and it helps us measure how fast galaxies are moving away from us. In fact, the expansion of the universe means that some galaxies are moving away from us faster than the speed of light. This seems counterintuitive because nothing can travel faster than light, right? But in the case of the expanding universe, it's not that galaxies themselves are moving through space faster than light. Instead, space itself is stretching, and this stretching increases the distance between objects at a rate faster than the speed of light. Because of this, light emitted from these galaxies may never reach us, as the space between us and those galaxies is expanding faster than the light can travel. This idea is one of the key points that Joseph Nieves, a theoretical physicist, has explored in his research. Nieves proposes that the expansion of space itself is a crucial factor in how we observe distant light. As galaxies move away from us, and as the space between us stretches, the light from distant stars and galaxies is stretched, making it harder for us to detect. In this way, the expansion of the universe itself impacts the observable universe, the portion of the universe that we can see or detect with our instruments. But the stretching of light isn't the only way the expanding universe affects our observations. The concept of redshift plays a key role here as well, As the universe expands, the wavelengths of light from distant galaxies get stretched, pushing them into the red end of the spectrum. Light from faraway galaxies that was once visible to us in the optical range is now stretched so far that it falls into the infrared or even microwave ranges. This means that even though the light from these galaxies may have travelled for billions of years, we may no longer be able to detect it with our current instruments, which are designed to observe light in the visible spectrum. The further away a galaxy is, the more its light is redshifted, and the harder it becomes for us to detect it. This is where the work of Max Tegmark and David Sloan becomes important. Tegmark, a cosmologist at the Massachusetts Institute of Technology, and Sloan, an astrophysicist, have both contributed to our understanding of the limits of the observable universe. They have shown that as the universe expands, the very limits of what we can observe are constantly shifting. In simple terms, there are regions of the universe from which light will never reach us, because the space between us and those regions is expanding too quickly. Their work emphasizes that the observable universe is not a fixed boundary. It's constantly changing as the universe grows, and as the light from distant objects is stretched beyond our ability to detect. These concepts, Hubble's law, redshift, and the expansion of space, are key to understanding why the night sky appears as it does. Even though the universe is filled with galaxies, stars, and light, much of that light is beyond our reach. The light from distant galaxies has been stretched, redshifted, and weakened by the expanding space between us and them, leaving us with a night sky that seems darker than we might expect. The darkness we see is not a sign that the universe is empty, but rather a reflection of the dynamic, ever-expanding cosmos in which we live. Light, like everything else in the universe, is affected by the space it travels through. As space stretches, so too does the light, shifting it to wavelengths we can no longer see with the naked eye. The further away a galaxy is, the more its light is stretched and the harder it becomes for us to observe it. This is a fascinating aspect of our universe, one that reminds us that our observations of the cosmos are limited by the very nature of space itself. The night sky, though filled with stars and galaxies, is also a reminder of how much remains beyond our reach. As our instruments become more powerful and our understanding of the universe deepens, we may one day uncover more of the cosmos that lies hidden beyond the observable limits. But for now, the darkness of the night sky remains a testament to the vast and expanding universe around us. At the end of the 20th century, scientists discovered a mysterious force that would completely transform our understanding of the universe's evolution: dark energy. This invisible force, which seems to push galaxies apart, is responsible for accelerating the expansion of the universe. Until the late 20th century, the general assumption in cosmology was that the expansion of the universe was gradually slowing down due to the gravitational pull of matter. But in 1998, two independent teams of astronomers made a groundbreaking discovery that would challenge everything we thought we knew. These teams, led by Saul Perlmutter, Adam Rees, and Brian Schmidt, were studying the light from distant supernovae, which are exploding stars. They had expected that the light from these supernovae would show a consistent pattern, with galaxies receding at predictable speeds. However, when they looked at the data, they found something astonishing. The supernovae were farther away than expected. This suggested that the universe's expansion was not slowing down, but actually speeding up. The force driving this acceleration was something entirely new, something that we now call dark energy. Dark energy makes up about 70% of the total energy content of the universe, yet it remains one of the most mysterious and least understood components of the cosmos. Unlike ordinary matter, which exerts gravitational attraction, dark energy seems to have the opposite effect. It pushes galaxies apart, counteracting the pull of gravity. This discovery led to a major shift in our understanding of cosmology, and for their contributions, Perlmutter, Rees and Schmidt were awarded the Nobel Prize in Physics in 2012. But despite their groundbreaking work, dark energy is still a puzzle. Some scientists, like Paul Davies, have proposed that dark energy might not be a force at all in the traditional sense. Instead, Davies suggests that dark energy could be an emergent property, a consequence of deeper, as yet unknown, quantum phenomena. In this view, dark energy is not a force that acts on matter like gravity or electromagnetism, but rather a result of the quantum vacuum itself, the mysterious nothing that fills all of space. According to this theory, the vacuum of space is not empty, but is instead filled with quantum fluctuations, tiny, temporary changes in energy that appear and vanish at the smallest scales. These fluctuations could manifest as dark energy, pushing the universe to expand more rapidly over time. Building on this idea, Ruth Durer, a cosmologist known for her work on dark energy in the early universe, has suggested that dark energy might be tied to the quantum vacuum's energy density. According to Durer's theories, the energy of the vacuum could be a driving force behind the acceleration of the universe. Essentially, the energy in this vacuum is everywhere, filling space itself, and its effects are felt on the larger scales in the cosmos. This concept ties together quantum physics and cosmology in a way that could explain how the expansion of the universe is accelerating. Yet, the idea of dark energy as an emergent property of the quantum vacuum isn't the only possible explanation. S. Perlmutter and J. A. Freeman have also explored the idea of quintessence, an alternative theory to dark energy. Quintessence suggests that dark energy is not a constant force, but one that changes over time. Unlike the steady, unchanging nature of the cosmological constant in Einstein's equations, quintessence proposes that dark energy could vary, potentially even slowing down or speeding up as the universe evolves. This theory introduces a dynamic aspect to dark energy, one that could evolve over billions of years, influencing the universe's future in ways we are just beginning to understand. The search for the true nature of dark energy remains one of the most pressing questions in modern cosmology. While it is clear that dark energy is driving the accelerated expansion of the universe, the mechanism behind it is still uncertain. Is it an inherent property of space itself, a product of quantum fluctuations, or something even more exotic like quintessence? These questions remain at the forefront of scientific inquiry, as astronomers and physicists continue to refine our models and gather more data. Dark energy's role in the cosmos is profound. It dictates the large-scale behavior of the universe, from the expansion of galaxies to the very structure of space itself. Its discovery has forced us to reconsider not only how the universe behaves, but also the fundamental nature of space, time, and energy. In a way, dark energy has become a window into the deepest mysteries of the universe, one that connects the large-scale structure of the cosmos with the strange, unseen world of quantum mechanics. As our understanding of dark energy continues to evolve, so too will our understanding of the universe's ultimate fate. Will dark energy continue to drive the universe apart, accelerating its expansion until galaxies drift beyond our observational reach? Or will the effects of dark energy evolve, leading to a different kind of cosmic future? These are questions that science is just beginning to answer, and with each discovery, we move a little closer to unlocking the secrets of the universe's most mysterious force. The speed of light is a fundamental aspect of the universe, and yet it imposes a strict limit on what we can see and understand. Light travels at a finite speed, approximately 300,000 kilometers per second, or about 186,000 miles per second. This means that no matter how fast light moves, it still takes time to travel across the vast distances of space. In fact, light from our closest star, Proxima Centauri, takes about 4.2 years to reach us. When we look up at the stars, we're not seeing them as they are in the present moment, but rather as they were when the light we see left them, often millions or even billions of years ago. This delay between when light is emitted and when we observe, it is one of the key reasons why our view of the universe is limited. The further a star or galaxy is, the older the light we're seeing. In essence, the farther we look, the further back in time we're seeing. This concept is known as look-back time, and it plays a significant role in how we observe distant parts of the universe. When we look at the Hubble Deep Field, one of the most detailed images of the distant universe, we're looking at galaxies that are billions of light years away, with light that's been travelling for that long to reach us. The light we see today from those galaxies is a snapshot of what they looked like when the universe was much younger, not the universe as it exists today. This time delay also explains why we cannot see the entire universe at once. Light from objects that are beyond a certain distance has simply not had enough time to reach us. The universe is about 13.8 billion years old, and in that time, light has only been able to travel so far. As the universe continues to expand, the distances between galaxies grow, meaning light from the most distant galaxies will never reach us. The farther we look, the more the universe stretches, and the less of it we can actually observe. This creates a cosmic horizon, an edge to our observable universe, that limits what we can see. But there's more to light's journey than just the speed at which it travels. Niels Bohr, one of the pioneers of quantum mechanics, introduced ideas that would radically change how we think about light and its behavior. Bohr's work on uncertainty tells us that, at the quantum level, there are limits to how precisely we can measure certain properties of particles, like light's position and momentum. This uncertainty adds an element of unpredictability to how light behaves. When light interacts with matter, such as passing through a cloud of gas or dust, its path can be altered in ways we cannot always predict. This creates additional challenges in observing distant objects, as light's path through space can be influenced by factors we cannot directly control or fully understand. This uncertainty doesn't stop there. The nature of space itself, as Roger Penrose and Lee Smolin have suggested, may also affect how light travels across the cosmos. Penrose, a renowned physicist, proposed ideas about quantum gravity, the idea that the fabric of space and time might be more dynamic and grainy than previously thought. If space itself has quantum properties, like a finely detailed structure at the smallest scales, then the very passage of light could be affected by the quantum nature of space-time. This means that in some cases light might travel through a space that isn't as smooth and uniform as we typically assume. It could encounter small quantum-level irregularities in the fabric of space itself, which could cause light to scatter, bend, or behave in unexpected ways. Lee Smolin has explored similar ideas, suggesting that space-time could be more fluid and dynamic than we think, and that quantum phenomena could influence how light interacts with it. If space is not entirely uniform, then light might not always travel in a straight line, and the universe might appear different depending on where and how you look. This could have implications not just for distant starlight, but for the fundamental understanding of how the universe operates at its most basic level. Another key factor affecting our view of the universe is the concept of redshift. As light travels through the expanding universe, its wavelength is stretched. This stretching causes the light to shift toward the red end of the spectrum, a phenomenon known as redshift. The more distant an object is, the greater the redshift and the more its light is stretched. Over extremely long distances, the light from distant galaxies can be stretched so much that it moves out of the visible range entirely, becoming infrared or even radio waves. This redshift is a direct result of the universe's expansion and adds another layer of complexity to our observations. Even if light from distant stars could reach us, it might no longer be detectable in the visible spectrum, making it difficult for us to see the farthest reaches of the cosmos. This leads to an important consideration in cosmology, the observable universe. As mentioned earlier, the universe is about 13.8 billion years old, and the speed of light is finite. Therefore, there's a limit to how far we can see. The observable universe is the region of space from which light has had enough time to reach us since the Big Bang. Beyond this point, we cannot observe anything, because the light hasn't had time to travel that far. As the universe continues to expand, this boundary grows, but there will always be regions of space that are beyond our reach, and thus beyond our ability to observe. Max Tegmark and David Sloan, two prominent cosmologists, have studied the implications of these limits and how they shape our understanding of the universe. Their work highlights the fact that the observable universe is not a fixed boundary, but a constantly changing one. As space expands and light continues its journey, the observable universe grows, but at the same time, objects beyond a certain distance, those that are receding faster than the speed of light due to the expansion of space, will never be visible to us. This concept helps to explain why, despite the vast number of stars and galaxies that exist, there are regions of the universe we will never be able to observe. The finite speed of light, the nature of space itself, and the limits of what we can observe all play a crucial role in shaping the darkness of the night sky. As we look into the vast reaches of the universe, we are not just seeing distant stars, but also peering back in time, observing the universe as it was millions, billions, or even trillions of years ago. The universe's age, size, and the limitations of light all combine to create a night sky that, while full of stars, remains mysteriously dark in parts, as much of the light from distant galaxies will never reach us. This cosmic horizon, defined by the speed of light and the expansion of space, serves as a reminder of the universe's vastness and of how much remains hidden from our view. When we gaze up at the night sky, we often think of stars, galaxies, and nebulae, dense clusters of matter and energy. But as vast as the universe is, it's also surprisingly empty in many places. These vast regions, which are almost devoid of matter, are known as cosmic voids. These voids are not just empty spaces, but are vast expanses stretching across billions of light years, where few galaxies, stars, or other forms of matter exist. They are the empty parts of the universe, but their emptiness is something that still plays a significant role in how we perceive the cosmos. Cosmic voids are thought to make up about 80% of the volume of the universe. These areas are so sparse that they are sometimes referred to as the supervoids of space. Within them, the density of galaxies can be a fraction of what it is in more densely packed areas of space. These voids are not entirely empty. There are still some gas clouds, dark matter, and isolated galaxies, but compared to the regions with galactic clusters, they are eerily devoid of matter. These voids are often situated between the filaments and clusters of galaxies, which make up the large-scale structure of the universe. The existence of these voids can help explain why the night sky doesn't look as filled with light as we might expect. In regions where galaxies are sparse, light from these galaxies has very little chance of reaching us. Galaxies within voids may still emit light, but because of the vast distances between them, much of their light is simply lost in the immense stretches of empty space. As the universe continues to expand, these galaxies move farther apart, and light from them has even less chance of reaching us. One of the scientists who explored the distribution of galaxies across the universe is William C. Saslaw, a cosmologist who studied how galaxies are arranged and why certain regions of space are more densely populated than others. Saslaw's research on galaxy formation and the large-scale structure of the universe showed that galaxies are not evenly distributed. Instead, they tend to cluster together in filaments, creating a web-like structure known as the cosmic web. These filaments of galaxies are connected by vast, empty voids, forming a giant network across the universe. These voids play a significant role in shaping the large-scale structure of the universe and contribute to the vastness and the perceived darkness of the night sky. Light from galaxies within these voids struggles to reach us for two key reasons. First, as the universe expands, the distance between galaxies grows. Light from galaxies located in these vast expanses of space may never have the time to reach us, as the space between us and them is increasing faster than the light can travel. Second, because these voids are so large and empty, there are fewer galaxies to emit light, so the regions of space between the bright galaxies are relatively dark. This makes the night sky seem dark in the places where voids dominate. In recent research, Ben Jones and Matthew D.K. Henry have studied the role that galaxy clusters play in filling the universe with light. While the voids are empty, galaxy clusters are densely packed regions where galaxies are drawn together by gravity. These clusters contain enormous numbers of stars, and their collective light creates bright spots in the night sky. Jones and Henry's research has shown that these clusters are essential in filling the universe with visible light, as their combined energy illuminates much of the observable universe. The cosmic web, with its clusters of galaxies and vast voids in between, explains why certain parts of the sky are bright, while others are filled with darkness. But voids aren't just empty regions that we ignore. In fact, they have a profound effect on the large-scale structure of the universe. Jean-Pierre Luminet, a cosmologist known for his work on cosmic topology, has proposed that the large-scale structure of the universe, what we see when we look at the distribution of galaxies, could be influenced by the very shape of the cosmos itself. Luminet's ideas about cosmic topology suggest that the universe might not be entirely flat, as it appears in many models, but instead could have a more complex shape, perhaps even one that is curved or multidimensional. According to Luminet, the cosmic voids and the dense regions of galaxies could be part of a larger structure that is influenced by the curvature of the universe. This could mean that the distribution of light across the sky is not just a matter of matter being distributed unevenly, but also a result of the shape of space itself. Luminet's theories raise the possibility that the large-scale structure of the universe, shaped by voids and clusters, could cause us to see some regions as darker than others. In this sense, the darkness of the night sky might not just be a result of the absence of light, but also a consequence of the universe's fundamental shape and structure. If the universe has a more complex topology, it could lead to regions where light from distant galaxies is bent, blocked, or even lost entirely to the structure of space itself. The cosmic voids, while seemingly empty, are far from simple. They play a crucial role in shaping the universe's structure, influencing the distribution of galaxies, and contributing to the darkness we observe in the night sky. These vast expanses of space remind us that the universe is not evenly filled with stars and galaxies, but is instead a complex dynamic network of voids and filaments that stretches across unimaginable distances. As we continue to explore these voids and the large-scale structure of the universe, we gain a deeper understanding of how the universe is shaped and how it has evolved over billions of years. The voids are not just empty spaces, they are essential components of the cosmic web, helping to define the universe's very nature. When we look out at the universe, we see an incredible amount of matter. Galaxies, stars, planets, and nebulae all lit up in brilliant hues. Yet, when we examine the universe's structure more closely, we come across something that doesn't quite make sense. There is far more mass in the universe than we can see. This invisible mass is called dark matter, and it plays a crucial role in shaping the structure and evolution of the universe. Despite being invisible and undetectable by conventional means, dark matter's presence can be inferred by its gravitational effects on the visible matter that we can see. Dark matter doesn't emit, absorb, or reflect light, which is why it remains elusive to our eyes and instruments. Yet, its existence became evident through the work of Vera Rubin, whose pioneering research in the 1970s forever changed our understanding of the universe. Rubin studied the rotation curves of galaxies, which describe how stars move within a galaxy. According to the laws of gravity, stars near the outer edges of galaxies should be moving more slowly than those near the center, because they are farther from the galaxy's center of mass. However, Rubin discovered that the stars at the edges of galaxies were moving at the same speed as those near the center. This was unexpected, and it suggested that there was additional, unseen mass that wasn't emitting light, holding the galaxy together and influencing its rotation. This observation led to the hypothesis of dark matter, an invisible substance that makes up a significant portion of the mass in the universe. The discovery of dark matter revolutionized our understanding of galaxy formation. Without the presence of this unseen mass, galaxies wouldn't have enough gravitational pull to hold themselves together. Dark matter is crucial in the early stages of galaxy formation because it acts as a kind of scaffolding. As dark matter clumps together under gravity, it creates gravitational wells that attract ordinary matter, helping to pull together the gas and dust that eventually form stars and galaxies. Essentially, dark matter is the invisible foundation upon which galaxies are built. Without it, galaxies would not have the structure they do, and stars and other matter would not have been able to come together to form the galaxies we observe today. But dark matter's influence doesn't end with galaxy formation. It also affects how light behaves across space. The gravitational pull of dark matter can bend light in a phenomenon called gravitational lensing. When light from a distant star or galaxy passes near a large concentration of dark matter, the dark matter's gravity bends the path of the light, distorting the image of the object. This is similar to the way a magnifying glass bends light to focus it, but on a cosmic scale. This phenomenon has allowed scientists to map the distribution of dark matter in galaxies and clusters, even though we cannot directly observe it. Gravitational lensing is one of the key methods used to study dark matter, revealing how it shapes the structure of galaxies and clusters across the universe. While dark matter is widely accepted as the explanation for these phenomena, not all scientists agree on its nature. John Moffat, a Canadian physicist, has proposed an alternative theory called modified Newtonian dynamics, or MOND. MOND suggests that the laws of gravity may need to be adjusted at very large scales, especially in regions where there is little visible matter, like the outskirts of galaxies. According to MOND, the observed rotation curves of galaxies could be explained by modifying how gravity behaves at these large distances, without invoking the existence of dark matter. While MOND provides a fascinating alternative explanation, it has not been as widely accepted as the dark matter theory, largely because dark matter also explains other phenomena that MOND does not, such as gravitational lensing. The search for dark matter continues, and its impact on the observable universe is profound. Though it remains invisible, dark matter is thought to make up about 25% of the total energy content of the universe. Ordinary visible matter, what we see around us, makes up only about 5%. The remaining portion of the universe's content is made up of dark energy, a mysterious force responsible for accelerating the expansion of the universe. Dark matter and dark energy are in many ways the unseen forces that drive the dynamics of the cosmos, but they also contribute to the darkness of the night sky. Because dark matter is invisible, it doesn't emit light. While it may help form the galaxies and structure of the universe, it also means that a large portion of the universe's mass cannot be observed directly. This invisible matter fills much of the cosmos, but because it doesn't interact with light in a way we can detect, it contributes to the cosmic emptiness that we perceive when we look out into the vast reaches of space. Even though there is more mass in the universe than we can see, we are left with a sky that remains dark in places, with the stars and galaxies acting as bright beacons in a largely invisible cosmos. Dark matter's invisible influence continues to shape the universe, guiding the formation of galaxies, bending light, and contributing to the structure of the cosmos. While we may not be able to directly observe dark matter, its gravitational effects are all around us, shaping everything from the rotation of galaxies to the expansion of the universe itself. It's a reminder that the universe, while filled with light and matter, also holds vast regions of mystery and unseen influence, forever hidden in the shadows of space. The universe is not a random scattering of stars and galaxies. Rather, it has a deeply organized structure. This structure is often referred to as the cosmic web, a vast network of galaxies and matter that stretches across the universe in filaments, clusters, and vast voids. The cosmic web is the largest known structure in the universe, a sprawling interconnected network that shapes the distribution of galaxies on the grandest scales. At the heart of this web are galaxy clusters, dense regions where galaxies are bound together by gravity. These clusters are like the intersections of cosmic roads, where galaxies gather, interact, and evolve. Between these clusters lie the voids, vast expanses of nearly empty space. These voids are where few galaxies are found, creating enormous gaps in the otherwise interconnected structure of the universe. The distribution of galaxies in this web-like pattern isn't just a coincidence. It's the result of gravity and dark matter, which have shaped the universe over billions of years. The formation of the cosmic web is a fascinating process. Ben Jones and Matthew D.K. Henry, two astrophysicists, have contributed important research to our understanding of this structure. They explored how the cosmic web affects the observable universe and the darkness of the night sky. Their research shows that the cosmic web doesn't just shape the locations of galaxies, but also influences the way we perceive the universe. Because galaxies tend to cluster together in filaments, these areas of high density are surrounded by vast voids. Light from galaxies within these voids can be obstructed by the very structure of the web itself, making those regions of space appear darker. It's as if the light is caught in a cosmic maze, where the brightest galaxies are concentrated in certain filaments and the rest of the space remains dark. This web of galaxies and voids also plays a critical role in the way light travels across the universe. The filaments of galaxies, as they form, act like bridges that connect distant regions of space. These filaments contain much of the visible matter in the universe, while the voids between them are largely empty. Light from galaxies that lie in the voids has a much harder time reaching us. The space between us and these galaxies is not just empty but vast, and the light from distant objects in these regions can be lost, scattered, or stretched as it travels across the expanding universe. This contributes to the observed darkness in certain regions of the sky, even though the universe is filled with billions of stars. Another scientist, William C. Saslaw, has made significant contributions to our understanding of galaxy clustering. Saslaw's work shows how galaxies tend to form in groups or clusters, influenced by the gravitational pull of dark matter. Dark matter, as we've seen, is an invisible but powerful force that pulls galaxies together, helping to create these large cosmic structures. Saslaw's work on the distribution of galaxies helps explain why the universe is not a uniform scattering of stars, but instead is organized into distinct clusters, filaments, and voids. The clustering of galaxies influences the distribution of light across the universe. In regions where galaxies are densely packed, light from those galaxies is much brighter and more concentrated, while the light from more distant or isolated galaxies in the voids is harder to detect. This clustering effect also helps us understand why the night sky appears as it does. When we look up at the stars, we are seeing the light from galaxies that lie within the filaments of the cosmic web. The regions between these filaments, where the voids exist, are much darker. light from distant galaxies in these voids struggles to reach us, either because the space between us and those galaxies is expanding too quickly for the light to keep up, or because it is blocked or scattered by other galaxies in the cosmic web. In addition to Saslaw's work, there are alternative theories about the structure of the universe and the way galaxies are distributed. One such theory comes from Jean-Pierre Luminet, a French cosmologist, who has explored cosmic topology, the shape of the universe on the larger scales. Luminet's ideas suggest that the universe might not be infinite or simply flat, but could have a more complex structure. He proposed that the universe could have a closed, multidimensional shape, meaning that the light from distant objects might be bending around the edges of the universe, creating dark regions in the sky that we cannot see into directly. This would provide a more complex explanation for the varying brightness of the night sky, as the structure of the universe itself could cause light from some regions to be bent or lost entirely. These ideas highlight that the observable universe is not just a random scattering of light. The large-scale structure of the universe, shaped by the cosmic web, galaxy clusters and voids, determines how light travels through space and how we perceive it. The dark regions of the night sky are not necessarily empty. They are simply parts of the universe where the light from distant stars and galaxies has a much harder time reaching us. The universe's structure, its filaments and voids, creates a cosmic dance, where light is both created and obstructed depending on where you look. As we continue to study the cosmic web, galaxy clusters and voids, we gain deeper insight into the grand structure of the universe. This web is not just a map of where galaxies are located. It's also a map of where light can travel and where it's blocked. The varying brightness of the night sky, from bright clusters of galaxies to dark, empty voids, is a direct result of the universe's structure. The darkness we observe is a reflection of the vast, interconnected nature of the cosmos, a reminder that the universe is not just a collection of isolated stars, but a grand, intricate web where light's journey is shaped by the very structure of space itself. Our ability to observe the universe, while extraordinary, has its limitations. The vastness of space and the immense distances between celestial objects present significant challenges for astronomers. The most fundamental limitation is the speed of light. Even though light travels incredibly fast, it still takes time to reach us from the farthest reaches of the universe. This means that when we look at distant stars, galaxies, and other cosmic objects, we're not seeing them as they are in the present moment, but as they were when their light first left them, sometimes millions or even billions of years ago. The current observational technology that allows us to peer into the cosmos, such as the Hubble Space Telescope, has vastly expanded our view of the universe. Since its launch in 1990, Hubble has provided some of the most stunning images of space, revealing intricate details of distant galaxies, nebulae, and other cosmic phenomena. It's given us a window into the farthest reaches of the observable universe, showing us galaxies that formed shortly after the Big Bang. However, even with Hubble's impressive capabilities, there are still vast regions of space that remain unobservable. The universe is expanding at an accelerating rate, and some galaxies are receding from us so quickly that their light is redshifted beyond the range of our instruments. This means that light from these distant galaxies will never reach us, no matter how advanced our technology becomes. Enter the James Webb Space Telescope, which is set to push the boundaries of what we can observe even further. Launched in 2021, Webb is designed to observe the universe in infrared light, which will allow it to peer through dust clouds and observe objects that are too faint or too distant for Hubble to detect. Webb will be able to look further back in time, observing the earliest galaxies formed after the Big Bang, and provide new insights into the formation of stars and planets. Its advanced instruments will also give us a deeper understanding of exoplanets and their atmospheres, potentially revealing signs of life elsewhere in the universe. However, even the most advanced instruments like Webb will still face challenges in observing the entire universe. No matter how much we improve our telescopes and detectors, there will always be regions of the cosmos that remain beyond our reach. The expansion of space itself, combined with the limits of light travel, means that the observable universe is, by definition, only a fraction of the total universe. As space expands, light from distant objects is stretched, making it harder for us to detect. Even Webb, with its advanced capabilities, will only be able to observe a small portion of the cosmos, leaving much of the universe hidden from our view. But the story of our observational limits doesn't end with the technologies we have today. Roger Penrose, a renowned theoretical physicist, has proposed a fascinating idea known as conformal cyclic cosmology. This theory suggests that the universe doesn't just expand and end, but rather goes through cycles, each one beginning with a big bang and ending in a kind of cosmic big freeze. According to Penrose, the current expansion of the universe will eventually slow down, and everything will become so diffuse that it will be impossible for light to travel. After a long period of time, the universe will then collapse into a new Big Bang, starting a new cycle of cosmic evolution. If this theory is correct, it might change our understanding of the observable universe. Instead of thinking of the universe as having a definite beginning and end, conformal cyclic cosmology proposes that it is in a continuous cycle, and that the limits of our observations are just part of this ongoing process. While Penrose's theory is still speculative and has not yet been widely accepted, it opens up intriguing possibilities about the nature of the universe and the ultimate limits of observation. It also suggests that the universe may be far more dynamic and cyclical than we ever imagined. If this model is correct, then the universe as we observe it today might be just one phase in an endless series of cosmic rebirths. The challenges in observing the universe are profound, and they remind us of how much remains beyond our grasp. Even with the most advanced telescopes and instruments, there are still vast regions of space that remain unobservable. The limitations of light travel, the expansion of the universe, and the ultimate fate of the cosmos all contribute to the darkness of the night sky we observe. Yet, with each new discovery and each new advancement in technology, we get a little closer to understanding the universe in all its complexity. The future of observational astronomy holds great promise. New instruments, like the extremely large telescope and the square-kilometre array, will continue to push the boundaries of what we can see. We are on the verge of learning more about the early universe, the nature of dark matter, the formation of galaxies, and the possibility of life elsewhere in the cosmos. While we may never be able to observe the entire universe, the quest for knowledge and understanding will continue, revealing new insights and helping us unlock the mysteries of the universe. The night sky, though filled with limitations, remains a canvas for exploration, a place where the wonders of the cosmos are waiting to be discovered, one breakthrough at a time. The age of the universe plays a crucial role in why we can't observe distant light, no matter how far our telescopes may reach. The universe, as we know it, is approximately 13.8 billion years old, and this finite age imposes a fundamental limit on our ability to observe distant regions of space. When we look at the stars and galaxies, the light that reaches us from these distant objects has been travelling for billions of years. But here's the catch. There are regions of the universe from which light has not yet had time to reach us. The vast distances between us and these regions, combined with the speed of light, mean that some parts of the universe are forever beyond our observational grasp. This is not just a technical limitation of our instruments. It is a feature of the universe itself. Light, while incredibly fast, still takes time to travel. The farther away an object is, the older the light we see. In essence, when we observe distant galaxies, we're seeing them as they were when the light first left them. This gives us a kind of cosmic look back into the past, but it also means that some galaxies, stars, or other objects are simply out of view because their light has not yet reached us or never will, due to the accelerating expansion of the universe. Jean-Pierre Luminet, a French cosmologist, has proposed some fascinating ideas about time and its role in our understanding of the universe. Luminet's work on cosmological models suggests that the way we interpret time in the context of the universe is far from straightforward. One of the core concepts he discusses is the idea of the cosmological horizon, which marks the limit of the observable universe. Beyond this horizon, light from galaxies has not had enough time to reach us since the beginning of the universe. Luminet's work on the structure of the universe suggests that the universe's size and age are deeply connected to the flow of time, shaping the way we perceive the cosmos. In a way, the universe is not just a space we observe, it is also a time we experience, and our observation of it is restricted by the amount of time that has passed since the Big Bang. The finite age of the universe means that our observations are limited to the regions of space whose light has had enough time to travel through the cosmos and reach our telescopes. For example, we can observe galaxies that are billions of light years away, but as we look further and further into space, we also look further back in time. The light from the most distant objects we can see was emitted when the universe was much younger. This concept of look-back time is key to understanding why the universe appears as it does. We're not seeing the universe as it is today, but as it was when that light first left those distant galaxies, billions of years ago. This brings us to the concept of cosmic location and its impact on how we view the universe. Our position within the universe, the fact that we are observing it from a particular point in space and time, means that our view is uniquely limited. The universe's expansion, combined with the finite speed of light, means that we are forever seeing the universe as it was, not as it is. In fact, we're always looking into the past when we observe distant galaxies, stars, and cosmic phenomena. Even the most advanced telescopes, like the James Webb Space Telescope, which will allow us to peer deeper into space than ever before, will still only give us a glimpse of the past, not the present state of distant objects. As our understanding of the universe deepens, we begin to realize that time itself might be one of the greatest barriers to fully comprehending the universe's true nature. We can measure the distance to stars and galaxies, and we can calculate their speed and movement. But the age of the universe imposes an inherent limit on our knowledge. The universe's history is written in the light that reaches us, but much of that history remains out of view, forever beyond our reach. The light from galaxies that are too far away or too distant in time will never reach us, and we are left with only the faint traces of the universe's past. This limitation of time isn't just a curiosity. It reshapes our entire approach to cosmology. It suggests that the universe is not just a static object we can study from a distance, but a dynamic, evolving entity that is bound by the flow of time itself. The age of the universe defines the limits of our observation and affects everything we know about cosmic history. It makes us realize that our understanding of the universe will always be incomplete, not because of the limitations of our instruments, but because of the fundamental nature of time. In this way, the darkness of the night sky isn't just a product of the absence of light, it's a reflection of the universe's age and the constraints of time. The further we look, the more we see the universe as it once was, and the less we see of its present state. Time, in its relentless forward march, defines our place in the cosmos, and the dark spaces between the stars remind us of the vast stretches of the universe that we will never be able to observe, not because they are hidden, but because they lie beyond the reach of time itself. As we've explored throughout this journey, the darkness of the night sky is not some strange anomaly, but a natural consequence of the universe's history. The very fabric of the cosmos, the way galaxies form, the vast voids between them, the expansion of space itself, and even the limitations of light, shapes the way we observe the stars. Whether it's the role of dark energy driving the accelerated expansion of the universe, the cosmic voids that block light from distant regions, or the finite speed of light that limits our ability to see objects that are too far away, each of these factors has contributed to the darkness we see when we look up at the sky. The theories we've discussed, from Olbers' paradox to cosmic inflation to the nature of dark matter, all help to paint a picture of a universe that is far more complex than we may have imagined. The universe is not a static, unchanging space, but one that is dynamic, expanding, and evolving. And within that vast evolving expanse, light travels across great distances, encountering obstacles, both visible and invisible, that shape the way we perceive the cosmos. Yet, as much as we know, there is still so much that remains hidden. Future discoveries, such as those enabled by the James Webb Space Telescope, are poised to expand our understanding even further. The ability to peer deeper into the distant reaches of space and time may offer us glimpses of the universe's early stages, answering questions we've only begun to ask. As we continue to develop new technologies and refine our theoretical models, our cosmic perspective will undoubtedly evolve, revealing new layers of complexity and wonder in the universe. But even as we learn more, there will always be mysteries that remain just beyond our reach. The limits of observability, defined by the age of the universe, the expansion of space, and the nature of light itself, ensure that some parts of the cosmos will always be hidden from our view. The darkness of the night sky will always remind us of how much we have yet to uncover, how much is still beyond our grasp. So as we reflect on the vastness of the universe and our place within it, let's embrace the unknown. The mysteries of the cosmos, whether they involve the nature of dark energy, the origins of the first stars, or the shape of the universe itself, will continue to inspire curiosity and exploration. The universe holds many secrets, and though we may never fully uncover them all, our journey of discovery is far from over. In the grand expanse of space, we are but small explorers, gazing into the darkness and searching for the light. And as we continue to reach out into the unknown, who knows what wonders await us? So, stay curious. The universe is vast, and it has much more to show us than we could ever imagine.